The next coordinate system we're going to look at are polar coordinates. And by definition, of polar coordinates are defined as an r-axis or a radial axis and a transverse axis or a theta axis, okay, where r goes outward from a fixed origin. So my origin is here. I can extend a line out, and r goes out from the origin. And my transverse axis, which is theta, is going to be perpendicular to that, rotating counterclockwise from that r-axis. So my theta axis is perpendicular going this way. So by definition, my position is simply the distance away from my origin in the r direction. Okay, so that's by definition of our polar coordinate axes. Okay, so now, of course, if I wanted to find velocity, I need to take a time derivative of position, and again, this axis follows my particle as it goes, so my unit vector, okay, does change with time. So I have to do the product rule, which is basically the derivative of r times the unit vector plus r times the derivative of the unit vector. And again, this derivative of the unit vector is a non-zero number. So as we did with normal and tangential, if I move to another point, okay, my UR was in this direction, and then it shifts and goes just a little bit up by some delta theta between 2 points on the path. Okay, and I can define this vector over here, delta UR, as just the unit vector 1, that magnitude, times delta theta. Okay, and that's basically the arc length here, and that's in the direction of u theta. So I can write delta UR equal to basically delta theta u theta, which when I put in terms of time derivatives, I basically get that the time derivative of the unit vector in the r direction is just equal to d theta dt times the unit vector in the theta direction. And I can write my velocity, therefore, as using this is r dot times the unit vector in the r direction plus r times what I have here, which is theta dot times the unit vector in the theta direction. So this, in using polar coordinates, is the definition of velocity. Now to go to acceleration, I take the time derivative of velocity, right? So I get r double dot ur plus r dot ur dot, right? That's just chain rule for this guy down here. Right here I'm going to have r dot theta dot u, okay, and then r theta dot u, theta double dot u, and then r theta dot u dot. Okay, so those are my chain rules here. Now, I already know the time derivative of ur. I found that right over here. What I don't know is the time derivative of u theta. The same basic idea holds true here. The only difference here is as I rotate around this path, okay, my delta u theta actually points in the opposite direction of ur, so I get this negative sign out in front. But it's still going to be theta dot times the other unit vector. It's just this one's pointing in the negative ur direction, this one's pointing in the positive u theta direction. So using this, as well as what I found out earlier about ur dot, I can take all of this and rearrange this top equation, linking up my urs, which will be this, as well as what I have over here, plugging in what I know about u theta dot, and I get that. And then the same thing holds true for u theta. So this is my acceleration, where the first one is the radial acceleration, the second term is the transverse acceleration. And it's all based on r dots and theta dots and whatnot, given right here. Okay. Now, in 3 dimensions, we have what's called cylindrical coordinates, and it's basically all I'm doing is I'm adding a z component. So you kind of think about maybe like a corkscrew, right? It's still r and theta going away, from some fixed origin, but then I just add a height to it as well. So really, it's the same equations, okay, just with a z, z dot, and z double dot in the uz direction. Okay, so if you've got 3 dimensions, you can add that z coordinate. Otherwise, just do the polar coordinates, and that's the kinematics using that coordinate system.